In calculus, we teach students this. So in calc, we teach that the integral from minus infinity to infinity is equal to the integral from a to infinity f of x dx plus the integral from minus infinity to a f of x dx if both of these things exist. Okay, so we teach this in calculus if both of these things exist, but now we're going to learn a different notion of the integral from minus infinity to infinity. So now we will define integral minus infinity to infinity differently to be equal to the limit as r goes to infinity of minus r to r f of x dx if this limit exists. Okay, so in the calculus definition of this, then we need this limit to exist. So this is the limit as r goes to infinity of the integral from a to r, and this limit to exist, it's the limit as r goes to infinity of minus r to a f of x, right? That's what we teach in this section in proper integrals in calc. Yeah, this is a different thing, right? So for every r, this is a meaningful expression, and we want this thing to actually have a limit at infinity. Yeah, are these things different? Can you give an example where these things give you different results? So if there is an example, it's going to be one where we can't take this thing and have it come to some answer, but we can take this thing and have it come to some answer. Yeah. So these are different. Can you give me an explicit one? The cube root of x is indeed good enough. Example. F of x is the cube root of x. So this is a nice odd function, exactly as you say. This thing is integrable from minus r to r, but if we try and take the integral from 0 to infinity, then indeed this is not integrable. Yeah? Good. All right, so what I did last time was this integral of minus infinity to infinity, 1 over 1 plus x squared. And I kind of skipped over this without saying it explicitly. I did this by saying, okay, this is the limit as r goes to infinity of minus r to r, 1 over 1 plus x squared dx. Yeah? And then I showed that this thing has a limit, and that was the answer. Yeah? In this case, is our Cauchy principal integral, principal value, whatever it was called, is it different than what we would do if we did the calculus 2 definition? Well, we got the same answer, but also this is perfectly meaningful for this integral because it's convergent, right? Yeah. So if we take this thing, we can break it up from the integral from 0 to r and r to 1 and just consider them completely differently. Yeah. So in this case, it makes no difference, but there are examples where it makes a difference. Yeah. So this definition, I've forgotten the name again, the Cauchy or whatever integral, this thing is a more general definition. This allows us to integrate a wider class of functions than we can when we do this. Okay? But every time we can do this, we can certainly do this. Okay? Cool. So with this notion of integrating from minus infinity to infinity, we can actually integrate a fairly wide class of functions. So what we need is the following. So suppose we integrate from minus infinity to infinity in the Cauchy sense this thing. Now those are rational functions. What would we need in order for the method we did before to work? So what did we do before? We took a semicircle like this from minus r to r. Look at this. We took the semicircle, right? And then it turned out that when we integrate our function, when this thing is turned into complex numbers, and when we extend it to the complex numbers, when we integrate over the semicircle part, that thing just vanishes as the radius increases. Yeah? And that's why we're able to reduce the complex version around the contour. So consider the integral from around this thing, call this entire contour gamma of r. So consider gamma of r of p of z over q of z. And this guy is an example of such a rational function. It turned out in this case, it was working out for us because in the limit, this thing turned into just the limit of this guy over here. But what was the property that allowed that to happen? What would we need in general from the p and the q? So let's write it out. So what is this? This is the integral from minus r to r of this thing. This is the guy we want. This is now just a real integral when we integrate over this part of the real line, right? And then it's this thing. Gamma of r, take away this thing. This is semicircle part. Yeah? And we want this thing to vanish. Yeah? So we're not going to use any. Go ahead. Yeah, but is that enough? So if we just take, so we didn't do anything to do with cancellation or anything. We just took the absolute value of the expression inside, right? So then the length of this guy right here is half the semicircle. So it's just pi times r. That's the length. Yeah. Yeah. So when we take absolute value inside, we're integrating over something which has got pi times r length. Yeah. And indeed, we want this function to get smaller as z goes further and further outwards, right? As the radius of the semicircle increases. But is that enough? Is that enough that it gets smaller? Are you saying that we just need that p of z over q of z goes to 0 as z goes to infinity? Will that be good enough? Okay. So if it goes to 0, like what rate would you like? So let's try and estimate this thing in the green box. So thing in the green box is less than the length of the curve, which is just pi times r. And then the supremum over this set right here of the absolute value of p of z over q of z. Yeah? Yeah? So what do we require? Mm-hmm. So what weight will it have to go in that case? So remember, it's a rational function. Yeah? So how far? What's the rate at which it goes to 0? So what I'm trying to say is, can it go, for example, to 0 like 1 over capital R to the 3 over 2? Is that possible? Yep, because the rate at which it decays has to be an integer, right? It has to be an integer rate of decay because the leading order term of this guy is z to something, the leading order term of this guy is z to something else, say z to the n, and this guy would be z to the m, yeah? So we'd need m to be bigger than n, yeah? And then the decay of this thing would be the absolute value of z times n minus n, yeah? Let me say that in the language of maths. So if p of z is equal to whatever coefficient, say a m z to the m, blah, 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 and then q of z is equal to, let's call them b, n z to the n, blah, 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 then n has to be bigger than m in order for this thing to go to 0, yeah? And the absolute value of P of z over Q of z is, for very large for very large z, we don't care about any of the other terms. They're insignificant. Yeah. So this will be like the absolute value of AM over BM. We also don't care too much about that. It's just a number. And then it'll be absolute value of Z to the M minus N. Yeah? And M minus N, let me put an example for very large Z. And let me even put a 2 here just to make sure it's true. So for very large Z, this will be true. And M minus N has to be an integer. Yeah? Has to be an integer. And that integer can't just be 1. Sorry, it can't just be minus 1. Because if it was just minus 1, then we'd have something here, which is like r to the minus 1 times r. Do you see what I mean? Yeah? Yeah? So then this integer, therefore, at least has to be equal to minus 2. At least has to be equal to minus 2 in order for this thing to have a hope to work. And then from this, we backward engineer what condition we need for this to work. We need that the degree of P to be less than the degree of Q by 2. Maybe better to say that. Degree of Q is degree of P plus at least 2. Yeah? So need degree of Q to be bigger than equal to degree of P plus 2. Yeah? Yeah? Cool. However, if we do have that, then this inequality I've done here does indeed give us that for very large, as we let r tend to infinity, this thing, sure enough, will go to 0, because this is for sure true, right? If we have some polynomial, then if we take the radius large enough, maybe I'll give you some details of this just in case it's not completely clear. Right? P of z equals am z to the m plus am minus 1 z to the m minus 1, and then so on. Then we can write this as a m z to the m, and then let's factor z to the m from everything else. We have plus like 1, and then a, let's not do it this way. Let's write it this way. Let's factor out a zm right at the front. So this is zm, and then we have am, and then am minus 1, and then we're going to have z to the minus 1, and then am minus 2, z to the minus 2, and so on. Yeah? So for very large z, this becomes more and more just like z to the m times am, because all of these terms here are just going down to 0. Yeah? And we do the same trick for q. So q of z equals z to the n, and I called it b, bn plus bn minus 1 z to the minus 1 plus a whole bunch of terms that will go down to 0. So then when we consider this p of z over q of z absolute value, then it is like the absolute value of m minus n, and then these expressions here. So the absolute value of am plus am minus 1 z to the minus 1 plus dot 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 over bn plus bn minus 1 z to the minus 1 plus dot dot dot, like this. Like this, right? Like this. Then what? Then for large enough z, we know that this guy will be less than, say, twice the absolute value of am. So just looking at the top, because all these other terms get negligible as the modulus of z gets bigger and bigger, we can guarantee that the top part of this quotient is less than twice the absolute value of am, so long as absolute value of z is large enough. Do you see what I mean? Yeah? Give me thumbs up if you do. Okay. And we can also guarantee that this bottom part is at least half of this guy, because all the other coefficients get arbitrarily small. It's at least half of this guy. Yeah, it doesn't matter what this bn minus 1 is and all the other terms. We can just guarantee that let me put it over here. Look at this. So absolute value of bn plus bn minus 1, z to the minus 1, blah, 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 all these other guys, by the triangle inequality is bn minus the absolute value of all these guys, blah, 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 blah. And we can make this arbitrarily small as z gets big. So then this is bigger than or equal to bn over 2. Yeah? Okay, so we have that the top half is less than twice the absolute value of am, and the bottom half is at least half of bn over 2. Yeah? For all large enough c. So then this entire expression here is less than, oops, it's less than mod z to the m minus n, and then twice am over half absolute value of bn, so then it's less than 4 mod z m minus n, and then this number here, am over mod bm. So better to put a 4. We can have any number bigger than 1, but the way I chose it, we have a 4. So now we completely have this for sure. Yeah? For all large enough radius, this estimate is correct. Yeah? And our assumption is that the degree of q, which is this n, is the degree of p, which is this m plus at least 2. So then this expression here is at least minus 2, and that's what we need. Yeah, that's what we need in order to just take the absolute value of this thing right here, yeah? And then we'll have some particular constant, this constant, mod z to some minus something, which is at least minus 2. Yeah, which will definitely kill the r. All right, so we should have been, everything should be completely like nailed down with certainty at this point. Are you with me? Are you with me? Yeah, okay, perfect. So that means whenever we have some expression like this, we can do exactly the same method. We can just create a semicircle and then show that the things we have on the degree of p and q mean that the upper part of the semicircle just go to 0.